So we now want to calculate the partition function. Let's say the canonical, we'll start off with canonical partition function of a single particle. And our first case that we are interested in is a free particle in a box of volume V is equal to L cube with periodic boundary condition. Right? So the task is now very simplified if we look at the momentum representation. Right? So in the momentum representation, I have the Hamiltonian is just a single particle is p square over 2m, and h of phi k is ek phi k, where the energy eigenvalue is h square k square over 2m. The coordinate, the wave function, the coordinate representation of the wave function, you know that it's ik dot r 1 over square root v, and this follows from the box normalization, where the vector kx, vector k is kx, ky, kz, which is 2 pi over L nx, ny, nz. Right? Now, assuming that this box is large enough, so these eigenvalues are typically discrete, right? And it depends on 1 over L. So if 1 over L is small, which means your box is large enough, then you can see that these eigenvalues, they lie very, very close to each other. Right? So you can imagine that, so you can consider them to be a continuous spectrum of energy eigenvalues that you have. Now the eigenfunctions are orthonormalized, which means phi k prime phi k is delta k k prime, and they form a complete set. Right? So now I want to calculate the density matrix in this momentum representation, and I know how to do that. So I have essentially rho hat phi of k prime, which is phi k e to the power minus beta h over z phi of k prime. And this is going to be minus beta ek over z phi of k phi of k prime, which is e to the power minus beta ek over z delta k comma k prime, which means that these matrix elements are diagonal in this. So rho of k prime is diagonal in this energy representation, which is not very, very surprising, right? So therefore, the partition function follows from trace of rho is equal to 1, that's a normalization condition, and one gets therefore z is equal to sum over k e to the power minus beta ek, which is sum over k e to the power minus beta h square k square over twice m. Now up to this is fine, but now in order to evaluate the sum, I realize that this vector k is equal to 2 pi over L nx, ny and nz, discrete values, but it goes as 1 over L. So clearly, if I have a large box that I'm considering, then these energy values are spaced very, very closely. So one can imagine that for a large box, I have a continuous spectrum of energy. So since the energy values are very, very closely packed, I can convert this into integral. I will write down z as explicitly zt comma v comma 1. I have just one particle, and this is going to be v over 2 pi whole cube. This discrete sum gets converted into this, into d cube of k e to the power minus beta h bar k square over twice pi m. This you can realize, this conversion happens because you know that in, let's say you take x direction, then nx, and between nx plus 1 there is only one mode. So 2 pi by L contains only one mode, right? So therefore from that conversion you see that this is in 3 dimensions, this is going to be 2 pi whole cube over L. So that is 2 pi whole cube over v. This has only one mode, therefore this integral comes out to be, if you go from the sum to an integral, you are going to use this. And if you do the integral, it's not very difficult to do, you are going to get v over lambda t, which is exactly the classical partition function for a single particle that we had evaluated. However, the difference is here lambda t will naturally appear and lambda t contains h bar. So the appearance of h bar happens quite naturally. It is not introduced in any ad hoc manner that you can imagine. It appears because of this form of the integral. That's it. In classical statistical mechanics, we had to kind of introduce it rather ad hocly, saying that, well, my micro number partition function, I'm going to take a log of that, therefore z must be dimensionless. But for such a system, hydrostatic system, or even for a single particle, free particle, I know that the partition function is an integral over momentum and coordinates, therefore it is dimension full, and therefore I divide it by 2 pi h bar, because p times q has the dimension of action and h bar also has the dimension of action, right? Good. But now, so essentially therefore I have rho k k prime is lambda t over v e to the power minus beta h bar square k square over twice m delta k comma k prime, right? Now the idea is that I want to evaluate the same density matrix in the coordinate representation. So in the coordinate representation would mean that I have r prime, rho hat, and then I have r, right? So this I can write down k, so I will write down r prime phi k, rho hat phi k prime r, right? So I introduce the completeness of this, and this quantity I already know, right? This quantity is, at least this quantity I know is k prime r prime phi k e to the power minus beta e k. We will just use that 1 over z, or rather let's explicitly use it, lambda t, sorry, so many stupid mistakes, lambda t over v e to the power minus beta ipsa k e k delta k comma k prime, and then I have phi of k prime r. So I can carry over one sum over k and take care of the delta function, so that I'm going to have sum over k r prime phi k lambda t over v e to the power minus beta e k phi k times r, right? Now phi k is minus I k dot r 1 over square root v, and phi k is 1 over square root v e to the power I k dot r, right? So that this sum is sum over k So I have lambda t over v times the sum becomes an integral d cube of k e to the power I k dot r prime 1 over square root v e to the power minus beta e k, and then I have 1 over square root of v e to the power minus I k dot r, right? So you see all of this, I have a factor v, then I have 1 over v. This cancels, square root v gives me a v, so I have 1 over lambda, so lambda t over v integral d cube of k e to the power minus beta h square k square over twice m e to the power I k minus I k dot r minus r prime. Let's look at the argument of the exponential. I have minus beta h bar square k square over twice m plus I k dot r prime minus r, which I take it as minus beta h square over twice m k square minus 2m twice mi over beta h bar square k dot r prime minus r, which is minus beta h bar square. This is a standard manipulation of a Gaussian integral, and k square minus twice mi beta h bar square k dot r prime minus r plus mi beta h bar square whole square r prime minus r, so that this argument becomes a complete square. And then you are adding this term, you have to subtract mi over beta h square whole square r prime minus r whole square times beta h bar square twice m. So therefore this integral, so this becomes k square, so we will write down straightforward as k minus k0 whole square. This gives you an I square as minus, right? So this is going to be, one has to be careful over here. This gives you an I square is minus 1, and then there is overall minus, so this becomes a plus, and therefore this is going to be minus m square beta square h bar 4 beta h bar square twice m r prime minus r whole square. So this becomes minus over twice m k minus k0 whole square. I cancel with the m, 1 beta goes out, 1 h square goes out. So I have m beta h bar square half r prime minus r whole square. So a little bit involved algebra, but nothing which you cannot do, nothing which is not doable. So your integral over here now is very nicely the matrix in the coordinate representation, the density matrix now takes the form as lambda t over v 1 over 2 pi whole cube integral d cube k e to the power minus beta h bar square over twice m k minus k naught, and note that k naught is mi over beta h bar square r prime minus r. right, whole square times e to the power minus m over 2 beta h bar whole square r prime minus r whole square. Now this integral is exactly doable. Now it's in a Gaussian form, and note that this measure is actually k squared dk. And if you evaluate this integral, so this is just square root pi by a for one dimension, I know, but this is now k square multiplied, therefore this is going to be twice pi whole cube. You're going to get 2m pi over beta h bar square raised to the power 3 by 2 times e to the power minus beta 2m h bar square r prime minus r whole square. Now of course it involves a certain limit of amount of algebra. If you carefully look at this, then this is just 1 over lambda t, right? Just simplify this, then you will see that this is going to be 1 over lambda t, and this quantity that you see over here is going to be lambda t, where lambda t whole cube is going to be capital lambda t. So just simplify this. This becomes twice m pi beta h bar square, and this term I can write 2 pi whole square times raised to the power 3 by 2. So this becomes 4 pi square raised to the power 3 by 2, and this is very easy to calculate now. Beta takes a kbt, m kbt, and then you have, this gives you 2, this gives you pi, 2 pi h bar square raised to the power 3 by 2, which is exactly your 1 by lambda t, right? Recall, in the classical statistical mechanics, when we did calculate your define this de Broglie wavelength, we said that this quantity goes as beta to the power d by nu. In our case, it's beta to the power 3/2, and therefore you have this as 1 over lambda t. And if you look at this quantity, this becomes pi times lambda t square, and therefore this is lambda t over v 1 over lambda t e to the power minus pi r prime minus r whole square divided by lambda t square, where lambda t whole cube is equal to capital lambda t, and lambda t is lambda t raised to the power 1/3 capital lambda t raised to the power 1/3, so that the expression for the density matrix in the coordinate representation takes a very neat form, which is 1 by v e to the power minus pi r prime minus r whole square divided by lambda t square. Now, if you look at it carefully, then you see that the diagonal elements, which is r rho hat r, is equal to 1 by v. And this quantity, so one particle in a volume v, and this quantity is nothing but the classical density, is the classical density. The transition probability, this off diagonal elements denote the transition probability from R to R prime, and these are your off diagonal elements of rho hat in the coordinate representation. Now as t tends to infinity, you know that lambda t vanishes, because lambda t goes as beta to the power 1 over nu. So in the limit of this, when lambda t, in the limit of large temperature, when lambda t vanishes, you see the off diagonal elements of this also vanish, right? So you only have the coordinate, you only have the diagonal elements. When t tends to 0, your lambda t tends to infinity, and that is when your off diagonal elements starts appearing, and you talk about a transition probability from R to R prime. So we have looked at the ideal gas free particle in a box, and for this particular case we computed the density matrix, in the momentum representation as well as in the coordinate representation. So we calculated phi k, phi of k, phi of k prime, as well as r prime rho hat r. Note that this representation phi k is identical to this presentation, and we will use this interchangeably. So the average energy is given by trace of rho hat h hat, which is going to be sum over k prime k rho hat k prime k prime h hat k, and this is e to the power minus sum over k prime, and there is a vector sign on top since we are looking at three-dimensional system, h square k square over 2m. The Hamiltonian is h square k square over twice m, and I have a z which comes from rho, and I have delta k prime k. So I can use one of the sums to take care of the delta function, and I have 1 over z e to the power minus beta h bar square k square over twice m h bar square k square over twice m. This, I know that the single particle partition function is v over lambda t, so this becomes lambda t over v. The integral over k can be again converted d cube of k, and I have h bar k square over twice m times e to the power minus beta h bar k square over twice m. So which means I have lambda t over v over 2 pi whole cube h bar square over twice m dk. This gives me a factor k square, and there is already a factor k square, so this is e to the power minus beta h bar square k square over twice m. If you substitute x as beta h bar square k square over twice m, then dx is beta h bar square twice m times 2k dk. So that k dk is going to be m over beta h square bar square times dx. So average of the energy is going to be lambda t over v over 2 pi whole cube h bar square over twice m dk. So I can use it as k dk times k cube, so we will just write it down as k times dk times k cube, and k dk is m over beta h bar square times dx. From this relation substitution, I know that k is going to be twice mx over beta h bar square, so raised to the power half, so k cube is going to be this raised to the power 3 by 2. So I have twice mx beta h bar square raised to the power 3 by 2 e to the power minus x, right? So everything comes out now. Lambda t v over 2 pi whole cube h bar square over twice m over beta h bar square, and then I have twice m beta h bar square raised to the power 3 by 2. I have dx x to the power 3 by 2 e to the power minus x. This I can express it in terms of a gamma function, and is going to be will give me a square root pi. So if I now simplify, this v is going to cancel out. All this factor, if you simplify, you will finally get that this is going to come out to be 3/2 kBt in accordance to the classical result.